and therefore I just asked that. So today we'll start the microwave engineering online class, and we'll be talking about some more fundamentals of microwave communication. In the last class, we discussed about the overview of microwave systems and basically about how they are used in the real world, and the applications, and what are the frequencies that microwaves function in, and so on. So, basically, as you know, microwaves are a type of electromagnetic wave. So, since it is a type of a wave, it is important to identify the characteristics, the properties of waves, and also define the mathematical function for such waves in order for us to design a certain system, and also find out parameters about the medium through which a certain microwave is propagating, and so on. So in this lecture, we'll be talking mostly about electromagnetic waves and how they are propagating in general. And if you have any questions, you can put in the chat. I will read them while I'm doing the class, and then you can get the answers. In the last class, I mentioned that for this course, we are having the mark allocation for the assessments in this manner. So I will be repeating this because I think some of the students were not there in the last class. So for the mid-exam, we'll be having 20% of weightage from the final grade or the final mark. And for the end semester exam, it will be 60%. And for the continuous assessments, we will be taking a total of 20%, and out of which we are giving 5% for the quizzes, 5% for the assignments, 10% for the labs. And also I need to mention that today I was hoping to give a quiz, but I thought that since this is the first time that some students are joining to this module, I will not be giving a quiz. So I will be giving some quizzes in the LMS, and you will be expected to do those quizzes during the time that I have allocated in the LMS to do those quizzes. So most of the time I will be doing those quizzes in the interactive sessions. Apart from that, it's very important to know that the reference books that I will be using when I'm doing this lecture and making the content in this lecture. So I'll be following this David M. Posa's book on microwave engineering. It's a really good book which has all the fundamental theories related to microwave engineering. So not only microwave engineering, but in general, it also talks about other electromagnetic waves and how a microwave type is related to the electromagnetic waves, and how the microwave is actually behaving like electromagnetic wave. Apart from that, you can also refer some other books that you can find related to electromagnetism, microwave engineering, and so on. So another book that I would like to refer is this antenna theory book, which is by Konstantin Balanis. So anyway, so let's start with the wave propagation. So the microwaves, since we are talking about microwave engineering, are also following the behavior of electromagnetic waves. And therefore, we need to understand the behavior of electromagnetic waves in order to understand the behavior of microwaves. And when we're talking about the generation of the electromagnetic waves, I don't know whether you have done this in the previous module, but I believe that you have learned something about varying electric field, and a varying electric field generating a varying magnetic field. And because of the varying magnetic field, another electric field is generated, and so on and so on. It goes on and on, and creates a propagating electromagnetic wave. So this phenomena is something that we can easily understand using the laws of physics. Right? Most of the laws that have been introduced by certain scientists like Faraday, Ampere, and also Gaussian law, we take into consideration in order to understand in what direction the electric field is getting generated, the magnetic field is getting generated, and the magnitude of such fields, and so on. So we need the help of those laws in order to identify and understand the propagation of electromagnetic waves, right? So when we are designing systems also, it is like if you are designing a microwave communication system, we need to know in what direction the electric field is present, in what direction the magnetic field is present, and therefore in what direction our wave is generated, and so on. Right? So once we give a certain power supply to, for example, a transmission line, right? So the transmission line in here, what I mean is something very, what do you call? I mean, you might think that I'm talking about the transmission lines of power systems, but in here I'm talking about the transmission lines in the PCB circuits, right? So in PCB circuits and in very minute circuits where we have microwave communication and signal generation, we supply some varying voltage, which creates a varying current. So because of this, an varying electric field is generated at the, the circuit. And then once the electric field and thereby the magnetic field is generated, and a wave is generated in a certain direction, right? So once we are like designing an antenna, for example, right? We want to know in what direction the antenna will be producing the wave, right? So in order for us to know those things, we need to know these laws that are given by these scientists who are good in physics. And we need to know that okay, this antenna will produce a wave in this direction, and therefore the maximum radiation will be in this direction, and therefore a certain like signal to noise ratio is possible in that direction at a certain range, and so on, right? So so once we are talking about not only antennas, but also access points like Wi-Fi access points, and the antennas in the phones, right? We have like antennas in the phones, which we connect to the cellular network, and also which will also connect to Bluetooth, right? So in all these instances, we need to like direct our signal in a certain direction, and we need to maximize the signal to noise ratio at the receiver end in order for the receiver to receive a certain signal in a reliable manner, right? Otherwise, I won't be getting any information from the signal I receive. So because of that, we need to make sure that our antennas, our access points, or the transmission lines, the equipments that we are designing are able to send the electromagnetic wave or the microwave in the certain direction that we want to send in, right? So basically a varying current produces a varying magnetic field, and that varying magnetic field is again creating a varying electric field. A varying electric field is creating a varying magnetic field, and likewise it goes like a propagation of rings, and then it forms the propagation of a wave in a certain direction, right? So I believe that part you have like covered in your previous module known as electromagnetism, right? So I'm just going through the overview of such concepts, and I'm going to be asking you questions related to be aligning them more towards the right. Can you like raise your hand if you have heard about Maxwell's equation? I'm not going to ask you anything. Just raise your hand in the reactions. I think you can give a reaction, no? In this. All right. Maybe you can't in Zoom. Can you do? Yeah, you can give reactions. You can give a thumbs up if you know, like if you have heard about Maxwell's laws in your previous module. Right? Can you give a thumbs up? Okay. There's one person who has. Okay, two people are there. Okay. Okay, so hopefully other people also have heard about Maxwell's laws, and you have learned a little bit or considerably in the previous module. So in this module, I will be explaining just the concept of these theorems. And I will not be like expecting you to do the calculations in the exam, but I will ask you to answer questions related to such calculations in the assignments. Okay, because like it's just like you're looking at the note and then writing the answer. So it's not going to be a big difficulty in that. So I will be like not asking, to derive, Maxwell's equations or explain or to write the equations of the Maxwell's mathematical, the equations in the exam. But I will ask you just in the assignments, those kind of equations. I will ask you to write answers in that fashion only in the assignments. So we'll be talking more about the applied part of the electromagnetic waves in this module. So, Maxwell's equations, right? So James Maxwell was a Scottish scientist, right? So he was able to understand the behavior of electromagnetic waves, and he was able to mathematically represent those electromagnetic waves. And because of these equations, we can identify or we can predict the behavior of electric and magnetic fields, which are generated by electric charges and currents, and also we are able to produce it in labs and environments, and prove the existence of electromagnetic waves. And also we want to we were able to find out not only the electromagnetic waves which are visible to us, but the electromagnetic waves which are invisible to us, right? So there are so many invisible electromagnetic waves which are even harmful to our bodies, and therefore it was possible using this because of this discovery of James Maxwell. And there's a German scientist called Hertz who was able to do the experiments and find out the existence of electromagnetic waves and also microwaves in his laboratory. And because of that, I think people were agreeing that these equations were actually correct. And then the Maxwell's laws, right? So Maxwell's laws, there are four main Maxwell's laws, and the Maxwell's laws are telling actually really simple things, although these equations look kind of scary sometimes, right? So actually, I hope you have gone through these equations. So I will just be going through the simple definition of these equations, right? The first law is saying that the total electric displacement through a surface enclosing a volume equals to the total charge within that volume, right? So when there's a closed volume, right? There are like when there's a closed volume and there's a some charge inside that volume, we can I hope you can see what I'm drawing. Okay. So when there's a closed volume and there's some charge inside it, let's assume there's a positive charge inside the closed volume, we can see that electric fields are generated from the positive charge to the outward direction, right? So once an electric field is generated in this fashion, the total electric flux that is generated is equal to the total charge that is inside the closed volume, right? So it is given by this equation, right? So this nabla dot E means the divergence of the electric field. So divergence of the electric field is equal to the total charge that is enclosed in this closed volume, right? So this is a closed volume, and the total charge inside is equivalent to the total divergence of the electric flux, right? Next, we talk about the Maxwell's Maxwell law 2. It is also similar to the Maxwell law 1. And in here, we are talking about the magnetic field, right? So once we are having, for example, like a North Pole or something, right? North Pole and South Pole, let's say, like normally magnetic fields are occurring when both the North and South poles are at the same location, or a location where there's no interference between those poles, right? So once like North and South poles are there, magnetic field is occurring from the North Pole to the South Pole, right? So if we like take consider a scenario where we have North Pole and South Pole in this fashion inside the closed volume, okay, so the magnetic flux is only staying inside the closed volume, right? The magnetic flux which are going outward from this closed volume is zero, right? So therefore, the total divergence or the total magnetic flux going outward from the volume is equal to zero, right? So if you have any questions, you can ask. I hope you are really good at this, right? Because you have learned about this in your previous courses, right? So and then the third law, right? The third law says that the total electromotive force that is created around a closed path equals to the negative time rate of change of the total magnetic flux through the surface body bound by that path. So when there's a like a closed path, for example, let's say it's a metal wire, like a closed metal wire, which is a closed path, right? And then we are sending or we are applying a magnetic field in a certain direction, and then the electromotive force that is created is increasing in the opposite direction, right? Because of this negative sign. Once we consider the magnetic field in the increasing in this direction, the electric field is created in this direction. However, the electromotive force is increasing in the opposite direction because of this minus sign, right? So otherwise we can take in the other way. Once the magnetic field is increasing in the negative direction, the electromotive force is increasing in this direction. So if you have any questions, you can ask, right? I'm trying my best to visualize these Maxwell's equations. And then we have the other option, right? We have the fourth law, right? The fourth law is talking about the magnetomotive force that is created around the closed path when we send a current across the surface that is bound by that path, right? So when there's a path which is having which is a closed path, and then there's a surface that is uh, that is bounded by that path, and when we assume there's some charges on the top of this this area, there's some charges, right? J means the charges, right? Electric charges that are on the surface, and then the total magnetomotive force which is created around this closed path is equal to the total current that we send through this surface, and plus the total actually electric flux that we send through this surface, and the total charge density on the surface, right? So the total electric flux plus the total charge on the surface bound by the closed path is known as the total gives the total magnetomotive force induced on the closed path. So those are the Maxwell's equations, and using those Maxwell's equations, we can understand, and we can say in what direction this wave is propagating, and how and in what magnitude such fields are generating, right? So we will see like the generation of the electromagnetic waves in this figure, right? So once we have like for example an antenna, right? So once we have as an antenna which is generating a certain like a magnetic field, right? Let's say this is the antenna, right? So we have a certain antenna, and then that antenna is having a varying current going through it, and because of that a magnetic field is generated around the antenna, right? So around the antenna, when the magnetic field is created like this, for each point you can analyze how the electric field is generated from the magnetic field, right? So this is the magnetic field generated around the antenna, which is having a varying current, right? Varying current. So this is the magnetic field, and this magnetic field is also varying in magnitude. And when you take each point in this magnetic field, right, we have like when we take the edge point, right, the magnetic field is going into the board, right? We denote it like a arrow sign. When it goes into the board, the electric field that is generated we can find using the Faraday's right hand rule, right? I hope you have learned this in your previous classes, but you can use Faraday's right hand law to find the direction of the electric field once you know the magnetic field's direction, right? So when we know the magnetic field is going into the board, we can find from the Faraday's right hand rule that the electric field is propagating in the direction governed by the by our fingers, right? So our fingers will be turning towards the clockwise direction, right? And then the electric field will be generated like this. And on this side, when we do the same one, but in here the magnetic field is coming out of the board, and therefore the electric field is going towards the this left side, right? So electric field is generated towards the like anti-clockwise direction. In here we have in the clockwise direction. So once we once we analyze this electric field also, we can see that once the electric field is going when we take a certain point in this loop, we can see the electric field is going down, right? So in that point, when we analyze again, we can see that the magnetic field is created in this perpendicular uh, direction in this manner, right? So we can define how our like magnetic fields are generated using our Faraday's right hand rule, right? So we can see that we can generate a chain of magnetic and electric fields on both sides of this antenna that will generate an electromagnetic wave. So this process will keep continuing until the strength of the wave is attenuated and it cannot produce electric and magnetic fields anymore. So so this is the phenomena that is behind the that is explaining us how an electromagnetic wave is generated. So